Alright, here's circular motion number 3. Key things that we need to remember. I'm just going to write them down right here. We have circular motion at a constant speed, then the unbalanced force toward the center of the circle got to be equal to mv squared over r, and the acceleration toward the center, therefore, since force equals mass times acceleration, is just v squared over r. All right. If just in case we need it also, the speed of something moving in a circle, remember from your lab, is the distance around the circle divided by how much time it takes to go around one time. Use that capital T for the time it takes for one lap. Okay, so let's see what number 1 has here. Woman flying aerobatics executes a maneuver as illustrated below. So she's upside down in the plane right here. Construct a quantitative force diagram, that means with numbers, of all the relevant forces acting on the woman flying on the airplane when upside down at the top of the loop. So, of course, there's force of gravity here. And that is going to be equal to 550 newtons. And then the seat in the airplane's upside down. So the support force, it sounds weird to call it a support force because she's upside down, but that is still going to be, it's perpendicular to the seat. The seat can't push up on her if the plane's upside down, so that is also going to be down. I don't really know at this point how big it is. We're going to have to work that out. But both of them are down. If you've ever been in like a roller coaster or on a roller coaster that goes upside down, you know that you can feel that feeling of the seat still pushing down on you when you're upside down. Okay, so, and it would be very possible to execute a maneuver like this without a seatbelt on. If you're not wearing a seatbelt, it's not like you would fall out. The seat is still pushing on you because of that circular motion and the force that way. All right. So what we need to do is figure out, first of all, that's the wrong units for our speed. So I'm going to convert that to meters per second. Divide by 1,000, multiply by 1,000 to get it to be meters, and then divide by 3,600 to get it to be seconds. It's about 65 meters per second, and all my other units are good. So the unbalanced force here, if you look at this, the unbalanced force toward the center, since the support force is now down on her, it's actually both of these are playing in the winning direction, and nothing is losing. So it's the sum of these two. And I know that when I've got circular motion, unbalanced force toward the center is mv squared over r. Mv squared over r. That is 611 newtons. Or, you know what, I'm going to just do 2 sig figs. I'm going to call that 610. So, I know now what the unbalanced force is. That's 610. And I know my force of gravity. So that means that this must be 60, right? Just doing a little algebra there. So I think my diagram was pretty okay. So the seat still has to push down on her to hold her in that circle. Okay. Number 2, 6 children run on a track with equal speeds. their masses are expressed in multiples of mass m, and their path radii in terms of, so the center of the circle's here, these two kids are running in a circle radius 4r, 5r, 6r. And there's the center. Rank the centripetal acceleration of the lettered children, A, B, C, D, E, F, according to largest to smallest. Well, centripetal acceleration, that's this, v squared over r. So I'm just going to make a little chart here. Centripetal acceleration does not depend on the mass of the kids, so I don't care about their masses. It just depends on how fast they're going, but they're all going at equal speeds, and then the radius. So v squared, which is the same for all of them, over whatever the radius is. So kid A is at a radius of 4r, kid B, radius of 5r, kid C, 6r, kid D, 4r, kid E, 5r, and F is 6r. Now, remember, like from the lab, the bigger the radius is, the bigger this number on the bottom, the smaller this is going to be. So these are the smallest when dividing by 6. I mean, the v squared over r part's the same for all of them. So the only thing we're really paying attention to here, if we want to rank these, are those numbers. So the biggest one is when I only divide by 4. So that's going to be a tie between A and D. Just put a circle around those to indicate that they're tied. And then dividing by 5, B and E are going to be tied. And then dividing by 6, C and F are going to tie. For B, rank the force needed for each one. Now the force, that's mv squared over r, so now the mass does matter. So it's the same as these, except now I also have the mass of each kid that I have to take into consideration. So I'm going to make my little chart again. And the same things here, except now I need their masses too. So that kid is 4m v squared over 4r. Kid B, mv squared over 5r. Kid C, 6m v squared over 6r. You can see this part's the same for each one of them. I'm just putting in the mass of each kid, right? E and F. Okay, so see the mv squared over r, since they're all going at the same speed, and the m and the r are just constants, whatever that is. The only thing that matters in comparing these are the numbers, right? So I'm just going to look at those. And so 4 over 4 is 1. 1 over 5 is 0.2. You can use your calculator for this if you want. 6 over 6 is 1. 2 over 4 is 0.5. 3 over 5 is 0.6. And 2 over 6 is like 0.33. So we want largest to smallest. The biggest is a tie between A and C. And then E and D, F, B. There's our ranking. All right. roller coasters use a hill for riders to gain speed, followed by an upside-down loop. Sometimes they do. Not any roller coaster that I go on. The loops are designed with large radius at the bottom here and a small radius at the top. And this kind of shape is called a clothoid. Answer the following questions, and we'll see why that's used. And in B, if you switch them, see why that's not a good idea. So the speed at the bottom here is 22 meters per second and 8 meters per second at the top. It should make sense to you that you would be going faster here, and then it's going to slow down as it goes to the top of the loop. You use quantitative force diagrams to determine the size of the force on the car by the track. That's the support force at the top and bottom of the loop. So at the bottom of the loop, we've got the car, of course, it's force of gravity, and then there's going to be a support force. The support force has to be winning here because there has to be unbalanced force toward the center of that circle, right? And then here, now this circle's down here, or the center of the circle, rather, is down here. So when you are at the top, now, kind of like the airplane in number 1, force of gravity down, and the support force also down. So here, unbalanced force toward the center of the circle is the normal force minus the force of gravity, and here the unbalanced force toward the center is force of gravity plus the normal force. Why is that true? Because the track, the support force, is going to be pushing down because the car is upside down. All right. Let's figure out what the mv squared over r is for each of these. The mass is 1,000. And for this one at the bottom, we're going 22 meters per second, and the radius is 10. That's 48,400 newtons. And filling in the details here now, I know the force of gravity is going to be 10,000, right? 1,000 times 10. So my unbalanced force equal to the normal force minus force of gravity. That's equal to 58,400. Now, if you want to figure out how many G's somebody is feeling, in other words, like how heavy they feel, the force of gravity is sort of like your baseline normal experience. Because usually, if you're just sitting there, if this roller coaster car is just like sitting and hasn't started up yet, like sitting on a flat piece of track, then the support force is just going to be balancing the force of gravity, right? So this is your sort of baseline number. And if you want to know how many G's, like how much stronger that force on the car or someone in the car is, you can compare this to this, whatever the support force is. So if you take this 58,400 and divide it by the force of gravity, then you're going to get about 5.8, right? And so that means at the bottom of this here, these people in this roller coaster car are going to feel 5.8 times heavier. That's a lot for a roller coaster. This is a pretty dangerous roller coaster. That's the point where like weird things start to happen to your vision, and like some people would black out with this much force on them. So you would not want it to be any more than that. And just note here that the bigger this radius is, the bigger that number is, the smaller this is going to be. So if this was like a smaller radius turn, that would be even worse for our poor roller coaster riders. Here, what about at the top? So I've got force of, the unbalanced force is going to be equal to mv squared over r. Mass is still 1,000. The v here is 8. And the radius of the smaller circle at the top is 5. That is 12,800 newtons. And so that's my unbalanced force equal to the force of gravity, which is still 10,000, plus the normal force. So here the normal force is 2,800 newtons. And remember, our baseline is this. So now people are going to feel lighter than they usually do, 2,800 compared to the 10,000. The second part of this problem, suppose a roller coaster had been designed with the small radius here and at the bottom and the big one there. Do all the same stuff and just figure out what the deal is then. Well, the diagrams would be the same, and what would be different would be this. Now at the bottom, my unbalanced force would be mv squared over r. So making that 5, that's going to double this. I think that's good math there. Looks good. And that means here, when I do my unbalanced force is equal to, that normal force has to be winning. So here, we are now going to have 106,800 newtons of normal force on that car. Now that is more than 10 times what the gravitational force is. So this is like more than 10 Gs of force. That is enough to make any human pass out and kill some of them, probably. So that is no good. That's why you need the bigger radius there. Now at the top, what if we put that 10 meter radius at the top? That's mv squared over r. Oops, I'm going to only go an 8 here. Sorry, I forgot to write the square there. I did it in the calculator though. Promise. So that is going to, if I double the number on the bottom, that's going to cut this in half. And unbalanced force here. The roller coaster can only push on them down, so that equation does not change. So 6,400 is equal to 10,000 plus that. Now if you look at that, if you subtract this over, now we get a normal force that's negative. What does that mean? That means that if this had a radius of 10 and it's only going 8 meters per second, that's not fast enough for it to like properly make it through that loop. In other words, you know, these days roller coasters aren't just like little cars that ride on top of tracks. They're kind of like hooked around the tracks, but it would be like hanging upside down off this. And on this, that would mean that the seat is not pushing on you. You would have to have the seat belt pulling up on you with this much force. So this is the kind of roller coaster, if you had this big of a radius and that slow of a speed, that at the top you would fall out. So that's also no good. So that is why we use this shape when we make roller coasters. All right. So we got an 80-kilogram person swinging here from point A to point B. Describe qualitatively, so that means not numbers, how the tension in the vine changes and why. Well, the unbalanced force is going to be connected to, literally, the tension, right? That's tension force in the vine is going to be what's, just like the support force in other situations, that's what's going to be pulling toward the center of the circle, which is right here. And that unbalanced force is equal to mv squared over r. So smaller r, a smaller number on the bottom means a bigger unbalanced force toward the center. And if that's got to come, at least in part, from that tension there, then that's why. So here, more tension than here. At point B, right here, he's swinging at 7 meters per second, and the vine's 8 meters long. How hard does he have to hang on to the vine to keep from slipping off? So he has, however much tension is needed there, that's how hard he has to hang on. That's basically just asking for the tension. So let's see. At point B, of course, gravity doesn't care what this dude is doing. And there's got to be unbalanced force toward the center, so that tension force has to be winning. So my unbalanced force equation would look like this. And unbalanced force is equal to mv squared over r when we got circular motion. So mass, speed, and radius. That's going to be 490, I think, right? 10 times 49. Now, that's not the answer to how hard he has to hang on. I still have to go back to this. That's the unbalanced force. 490 is equal to how much gravity is there on this guy? 80 times 100. So force of tension is equal to 1290. Now, if you think about, if he was just hanging on a vine, like hanging on a rope like this, and it's not moving, then how hard would he have to hang on? Well, he'd have to support his own weight. He'd have to hang on with 800 newtons. He'd have to just match the gravitational force. And once he starts swinging, because this unbalanced force that's required toward the center of the circle, then the force of tension increases. He's got to hold on with that force of gravity plus however much unbalanced force is required. If you've ever gone on like a rope swing that goes out over a river or something like that, you know that as you swing down and you start to swing faster and faster, it becomes more and more difficult to hold on. You feel like you're heavier, and this is why. So he has to support, like, he's feeling like he has to support himself plus about another half of himself. A moment later at point C, the line catches on a branch, reducing the radius to 2 meters. If you reduce this to 2, that's going to quadruple this. So now the unbalanced force on him is, his mass is the same, his speed is the same, but now that's only 2. So that's going to be that. And when I put that in this same equation, unbalanced force is that tension force minus the force of gravity. adding the 800 over to the other side there. So now he has to hang on with 2,760 newtons of force. And usually, remember, if he's just hanging there and the rope's not moving, he just has to support himself. So like the normal amount is 800. So if I divide that number by 800, that gives us like a sense of how much. That's about 3.5. So he has to support like 3.5 of himself there. That is difficult to do. You can imagine like hanging on this rope here with 2.5 more versions of yourself. What you want, top half or bottom half? There, top half, right? So that's what that would be like when the radius becomes shorter like that. And then part D, if Tarzan slips off point C, what path would he take? If he slips off here at C after he's gone slightly up there, then it's kind of a throwback to Unit 6. He would just become a projectile and follow like a parabolic path like that. At point C, he would be very slightly going up. So it would be like he had an initial launch, an angled launch like that. All right. Last page. We got these 6 kids again, except this time they all have equal masses and their velocities are different. So the centripetal acceleration is v squared over r. So let's rank them. Let's see. So the first kid is 4v squared. The whole thing is getting squared, not just the v, right? Their velocity is 4v, so the whole thing's getting squared over 4r. Kid B, v squared over 5r. Kid C, 6v squared over 6r. D, 2v squared over 4r. E, 3v squared over 5r. And F is 2v squared over 6r. Okay, so kind of like what we did in, was it number 3? The last time we looked at this ranking kind of problem. We just simplified the number part of that, because the v squared over r part is going to be there for all of them. So here I've got 4 squared divided by 4, which is 4. Here I've got 1 squared divided by 5, that's 0.2. Here, actually, let me put these up here, I get a little more room. Here, 6 squared over 6 is 6. 2 squared is 4 over 4, that's 1. 3 squared is 9 over 5, that's 1.8. And 2 squared 4 over 6 is 0.67. And then we just have to rank them from biggest to smallest. So C is going to be the biggest, and then A, E, D, F, and B. No ties. And then here, for B, rank the centripetal force. Well, the unbalanced force toward the center, that's what centripetal force means, unbalanced force towards the center, is mv squared over r. Now, all these kids have equal masses. So if we take this ranking of kids and we multiply all these things by the same mass, that's not going to change the order because they all have the same mass. If this is the same for all of them, it's going to be the exact same order. So I don't think I need to go through and do that again. It's just the same. And the last one. an amusement park ride operates as follows. You ever been in this one? Sometimes it's called the roundup, where you go in and the thing spins around like this. Standing against the wall, cylinder begins to rotate, and when it's up to speed, the floor drops out. Sometimes you have that floor dropping out. Sometimes it's just like a cage, and the floor could drop out, but it doesn't have to. You're pushed up against the wall anyway. All right, to determine the period of rotation necessary to keep the riders from sliding down the wall. Okay, so this is the coefficient of friction here. The typesetting is a little bit weird there. So if you didn't figure out what was going on there, I'm sorry about that. That's our coefficient of friction. So what would, I'm going to do a force diagram for the rider when the rider is like right here up against this wall. What would the force diagram look like? Well, of course, there's force of gravity. And on this rider here, it'd be 730 newtons. And then there's got to be some force toward the center of the circle, which is here in the middle of the ride. What force is that? Well, this person is pinned up against this wall. So the support force from this wall is this way. It's perpendicular to that wall. So this is the support force. And what's stopping them from sliding down here? Because they're moving in a circle. They're not moving in this direction. So that means the forces in this direction here must be balanced. So what is this force here? Well, that's the force of friction. It's stopping them from sliding, right? And if they're not moving in the up-down direction, then that must be equal to that, right? Okay, well, we know that the force of friction is equal to mu times the normal force. So I think I know 2 out of the 3 things in this equation. So that normal force on them is going to have to be equal to 1,460 newtons. And once we know that, this is the only thing that's pointing toward the center of the circle. So that unbalanced force toward the center of the circle is coming from this and this alone. So that means that my mv squared over r must be equal to that normal force. And I know the radius of the circle and the mass of the rider, so the only thing I don't know is how fast. Now, this didn't ask for how fast. It said determine the period of rotation. That's the amount of time it takes to go around one time. If you're thinking to yourself, geez, this is a hard problem. This is the hardest problem in this assignment and probably a little out of range of test difficulty. So you understand everything that we're doing here by the time we get to the end, then I think you're in good shape. It'd be unlikely for you to see something quite this tricky on test. So 1460, just doing some algebra here, you're going to multiply that r up here, divide by m, because I know how to do algebra, and then I take the square root of all that to figure out what v is. You know that passing Algebra 2 is a prerequisite for taking this class. I let a kid in once who did not have Algebra 2. Boy, it was not pretty. I'll tell you what. So the speed of the rider going around that circle is 5.5 meters per second. And this is maybe the first time we're having to use this idea. All these equations will be on your test, of course, that speed is equal to 2 pi r, the circumference of the circle, divided by the period. So the speed here, 5.5, is equal to 2 pi times the radius divided by period. So just doing a little bit more algebra there. Almost made it in by the bell. Is 2 pi times 1.5 divided by 5.5. And that gives me a period of about 1.7 seconds. That's how long it takes for this ride to revolve one time, given that it's going fast enough so that the person's going to be held up on the wall. All right. That was a tough one. See you later.